It was a few weeks ago. A guy named Pap, we'll call him Ethical Pap, released a video titled Reverse Engineering, blah, blah, blah. I don't know what he titled this video. I should have checked that. And he just released it. You know, why not? It was well received. A lot of people saw the video, and despite the fact that Ethical Pap
absolutely butchered the history of the bomb
and then had to pin the comment so that others can see the clarification there. I don't know why more people didn't roast him for that, but he got a lot of good feedback for it, and he got a lot of great feedback for the entire video, the reverse engineering video. Now, of course, there was subtle mistakes, but we're going to actually correct a lot of those mistakes. Ethical Pap is going to correct a lot of those mistakes in this video, including the Little Indian format that was subtle. You didn't see in the first video. I talked all about Little Indian, and towards the end of the lab there, I used Big Indian instead of Little Indian. And with this video came a lot of feedback, compliments, a lot of suggestions, ways to improve. There's a lot of stuff that came. I read those comments. Ethical Pap read those comments because this story is about Ethical Pap, not me. So what did Ethical Pap do about the comments and feedback and suggestions and all of the above? He took it all, he kind of molded it together, and he formed a masterpiece. And we call that masterpiece Reverse Engineering Part 2, blah, 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 whatever this video title is going to be. Ethical Pap hasn't figured that out yet, but this is going to have more static-based analysis. We're going to look at some practical labs on reverse engineering, things like cracking serial codes, things like reverse engineering basic applications, so that you can see the process. We'll use things like breakpoints, dumping registers at a certain part in the application process so we can see what is being stored in these registers and grabbing context. It's really fun. I love making these videos. I hope that you guys can learn more from this, the static analysis part 2, because to be honest, although part 1 was entertaining to watch, it only scratched the surface of reverse engineering, and the purpose of it was to get people excited again about learning. So Ethical Pap had that mission that he did, and here we are again. I have started working on a dynamic analysis video so that you can see how to analyze applications from a dynamic perspective. Usually when I'm like reversing some kind of software, I start with dynamic, clicking buttons, writing down what I click, things like that, and then we go backwards into the static analysis so that we can have more context. But when learning, we're learning backwards. We're learning static first and dynamic later, so that's interesting, but I hope you enjoy. And without further ado, let's jump into the video. I almost forgot. One more quick thing before we start this video. Disclaimer, it is actually not legal to just go cracking legitimate software, especially if it's licensed and closed source. So don't go doing that, all right? We're ethical here. We do things ethically. As such, I didn't want to go and start cracking real software in a video like this. So I had to, surf the internet and see what I could find. And I came across a GitHub page by CSP Instructor. I'll link it in the description. But this GitHub page actually had several different labs that you can utilize to crack different software that this CSP Instructor person made. So shout out to him, whoever you are. I appreciate you. And yeah, I'm using those labs in this video to show some things. One other thing I want to mention is that labs, of course, aren't actually as complex as the real world. For instance, I love to look for the main function when trying to figure out how software works. The main function is more often than not obfuscated or just plain hidden, so it's hard to find when you're actually running things through the disassembler. There are times where the disassembler might error out, so you're not actually able to completely disassemble this code or anything, especially from closed source software. There are methods to kind of still be able to work around things. You can manually try to work through the errors to complete the disassembler. If the main function is missing, you can run the software, maybe look for strings like main string. Sometimes even though the assembly language is obfuscated, there's a main string that's pushed into one of the registers, and that register is used to, hold the main function or call, the main function is called from that register. So there are little tricks like that that you can use to find the main function and all these other things. If you can't find main and you're really lost, start with entry 0, entry point. You can't go wrong with there. That starts at the very top, and you just start working your way down, setting breakpoints, looking at the registers, at what's inside of them at different breakpoints, and you start jotting down what's going on. As you use the application, look at different strings that the application has, search for those strings in the disassembler, right? And then see what's happening on the assembly language side, and that can help you kind of map out how this application looks in assembly. So a lot more complex in the real world, but you can actually make it simple by taking your time and just really mapping out these things. Reverse engineering actually takes a long time in real life. In fact, so long that it can take a few days, weeks, sometimes months. I've analyzed malware that took me several days. It was just basic malware, wasn't that complex. So just keep that in mind. Okay, all right, all that out the way. We're really jumping into the video now. Let's dive in. All right, so this is a just like a basic software, basic like serial software where you just enter a serial number and it checks that serial number. And let me just run it to show you what I mean. It'd be a lot easier. All right, so we run this, we can just here. So this is pretty much what it is. You enter a serial key. It could be anything. You check that serial key and it tells you if it's wrong or right. That's pretty much all the software does. The idea is for us to see if we can crack the software and get the serial key to log in. And we're gonna be doing that with, of course, Cutter. So debugger process finished. Let's start from here and let's work our way through this program here. So the first thing that I like to do is look for the main function. Not needed, not necessary. Some people like to look for entry, which is here, but entry is pretty big. So I like to look at the main function and see what it is that we can learn from that. And then once we click on main, I like to go to the graph of main. From here, we kind of figure out, okay, what's going on at like an overview kind of thing. So for example, we see, okay, well, now we're pushing something to the stack. EBP here, keep going down, you start to see a bunch of pushes and a function call. Well, this is a create dialog param a function call. What we can do here is actually just throw that into Google. Create dialog param a, create dialog param a, and that kind of gives us dialog box, which of course is the dialog box that we saw, and displaying information in that dialog box pretty much. So we're reading Little Indian. This is Little Indian format. In fact, we can go to our dashboard and learn some information before we continue. So PE format, portable executable. There's the 32-bit here, which is the 32-bit is the x86 architecture that we had gone over in part 1, which is why we're sticking with 32-bit now. We have, this is just the modes, operating system, of course, Indianness right here. So Little Indian is auto detected by Cutter. So when we read the main function, we are actually going to be reading these pushes backwards. So create dialog box, we can check here and we see we have params, we have the dialog function or process, we have the parent and template name. So going backwards, right? So we have that instance that right here. First one on the bottom is the one on the top with Little Indian. So we have the H instance here, as you see right here. And then going up one, we have the template name, and then that corresponds here. So Little Indian format. Then we have the parent going up one, and then dialog, of course, and then the GW init param here. So my guess is this is the dialog box that we get when we open a box that has that serial number. The box pops up first, and then you have like text load, and you're probably going to see like create dialog box param a. Then you'll see something like right here, like dispatch message, things like that. So it's going to be a lot of text that goes into this. Okay, so for this one, since we're cracking, I like to work backwards. So we're going to actually run this. Boom. And we will let this pop up. And I like to enter, it can be anything. So we'll just give random values here. Check, and we're going to work backwards. So we get this message, wrong serial key. So this is where I'd like to start first and then work backwards, see if we can find out where this stuff is. So in order to find wrong serial key, I'm going to actually go to strings, and I'm going to search for the string wrong and see where it is. Yep, here it is. So wrong serial key, and then we can show the reference where it is. So this is being referenced. So this right here, message box A, and then you have your information here. So I'm going to actually copy this address here, and I'm going to type that in at the top because I want to find where that is in our code, which is here, the first one. So let's scroll up a little bit. And then we can look at message box A, right? So if we wanted to, we could message box A. just the Windows API function here. And then we read, little Indian. So push 0, which would be the first one. This WND thing here, it's I don't know what this actually is, but it's a 0, so we don't actually need to worry about that at the moment. And then the next one is a string that's being pushed, wrong serial key, try again. And so that's the what's known as LP text, and we can look down and see if we can find a reference. So looks like the message that's going to be displayed, pretty much the LP text here. And then the next one is the caption here. Sorry, so that's also going to be a displayed message. It's going to be displayed as a caption. As you can see, LP, it says LPC STR, and then if you look here, the type, this is just a message to be displayed. So we know that these two will be displayed. And then the uint is not specified. So that's not specified. So it's the U type here. Looks like that is, yep, looks like that's not really specified there. So we know this is going to be a message displayed, which is, the message that we got when we ran the program. So we know that. But what we're looking for is we're actually looking to scroll up and see if we can find a function call that might be related to some kind of comparison, if that makes sense. So we have another message box, and then above that we see some strings. Congrats and well done. So that tells me that this block here is the end result of either a well done or, sorry, try again. So that means further up, there has to be some kind of comparison or something that's being done here to compare what we entered to something else. And we're going to try to figure out what that actually is. So one thing we can do is keep going up and looking for, this is the well done. So it's basically using the same thing, message box A. So we're going to go up and look for these jumps, and we're going to look before the jumps and see what's happening. So there's an arithmetic logic XOR, right, for 2 EAX. We're going to keep going up and seeing things. Then there's a test. A test is like another arithmetic logic. It's like an AND. So it's kind of like ANDing these two together and comparing if they are the same. And if the J and E is like jump to this address if the condition is not met. So it's basically saying if not, true, jump to this address. So if this test here does not evaluate, then we're going to jump to 110, which is here. Did I get that right? 401, yeah, which is here. And then this does a comparison. And then if it doesn't meet, it jumps to the 130, which is here. And then this is also another. So SBB is like a subtraction. So this is basically subtracting to integers, and then it continues to go down, and it looks like it does another test. If the test is negative, it jumps again down to 154 here. And if the test is positive, it looks like it's jumping here. So this test is that conditional, but we're going to work backwards for what we just said to see if we could find out what's happening here. So I think the comparison that we first saw was this test here, DL, but DL is like it's like a data register. So I want to go up and see if we can find our general registers that is assigned to DL. So let's actually follow DL, see if we can get it up here. So DL EAX. So right here, EAX is something's going inside EAX, and then it's moving inside DL. So what we can do is we can set a break point here. And a breakpoint is pretty much just a way for us to execute our code, and then we stop it at a certain point in assembly. I like to use it because we can then see what's inside of our registers, and then we can start deducing what's going on from there. Okay, so we know that something goes inside the DL data register here, and that value has to be an EAX at this point. I am actually, do I want to break here? Let's remove that. Let's break here right after that. Right after this goes in, so we can see what's inside of this EAX. Yeah, let's do it this way. Okay, and I want to set another breakpoint. So after this moves the address here inside of EAX, then we go to move this into DL, and then we compare DL with ECX when ECX is declared here first, which is assigned a string of cracking lessons, which my guess is this is the string that's being compared with whatever we enter, which means if it doesn't match whatever this is, it's going to fail. So this is technically our serial key that we'll need, but we need to just make sure that this is, this is exactly how it is. It should be, but we'll keep going and make sure that what's in the register ECX is exactly what should be evaluated here. Yeah, here at the comparison. So we're comparing the bytes of ECX to DL. So to do that, we can set a breakpoint here. Boom. Okay, now we run it. Let's cancel this and then let's run, and we should get hit in our breakpoints after the dialog box comes. So dialog box, and then we're just gonna type something that we'll know. So we'll say I don't know, pap v. We'll say pap. There it is, pap, and then we'll check, and that stops our break. It hits our first breakpoint, which is a D word. All right, so now that we are at our first breakpoint here, we can actually go to where are we? Debug, view, and then we can look at the registers. We actually can I think there's a register view. No, there's not. Let's see, debug, view, registers. I thought there was a view where show and no. There is a, maybe I was just seeing things, but I could have sworn oh, register references. Here it is. So yeah, there is a view where we can see all of our registers. So one thing I want to point out before I actually show these registers is that Cutter is like built on like a 64-bit architecture, and this x86 based program here is a 32-bit architecture. So some of the registers may not line up, or what they may not appear to line up, but they're pretty much the same. So for example, EAX, for example, you might see as RAX. R is just so E is the extender for the 32-bit. R is pretty much just assigned for like 64-bit registers instead of 32-bit, so it extends that even further. So when we're looking for what's in the comparison here, we are actually looking for like R. We'll say like probably like RCX at this point. And then if we're looking here, instead of EAX, we're looking for what's in RAX. And it should be what we entered inside RAX. So if we go to the register, we look for RAX. Yes. So we see PAP. So that's what we entered. And then if we go to the comparison here, we're comparing RCX to DL, and we put what we registered, right? We put ECX, sorry, we put EAX here. This is what we registered inside EAX, or the value inside EAX is PAP, and we move this register inside of the data register DL. And then from here, we are comparing DL with ECX. So we're pretty much comparing EAX with ECX, but for the Cutter debugger, confusing, I know, it's really RAX with RCX. So if I go to the risk register here and I look at RCX, that's ECX there, and we see what's inside of RCX at this point during the comparison. So it's basically now comparing PAP with this string. Pretty sure I can just copy this, but we'll type it out. All right, so it's comparing these two, and I'll do like a comparison. There it is. And then it's saying, all right, so this is a jump condition. So if it's saying if it's not, if the comparison is not true, then we want to jump to 130, which is here. But in this case, it is true. So we're actually not going to jump. And then it does another comparison with DL itself. If that's not true, it jumps, but we are true now, right? So then it starts to move a value of EAX plus 1 into DL, and then it does another comparison of ECX plus 1. So this is another comparison and just adding the integer to it. That's not true, which it is. It is valued as true because in this case, we'll say instead of PAP, we're using, the true value. So we're using something like that. We're using like that. Normally this would not be true and it would jump down to the false wrong serial key here, but we're saying that it is true. If that is true, then we end up going further down. So test here, that's true. So it goes down, XORs. If this is true, then it jumps to 135, and 135 is here. So then it pushes 0 to the stack. From there, it does another AND operator, a check between EAX and EAX, so the same register. If that's not true, it goes down, which we know this is true because they match. So this is like a another comparison, and then it pushes the congrats, well done. So this evaluates correctly as we're reading it, as we're going down. If we actually rerun this, so I'm actually gonna we'll forward this, and then we'll forward through again. Okay, so now that we forward, actually what we'll do is this. We'll run. Okay, actually let's do this. Let's remove the breakpoints if I could find them. Let's see, view. We will remove this breakpoint and then remove this breakpoint. Okay, now we can run this. Boom, and we get the dialog box here. We have already figured out that the check is actually this string here from that RCX register, which is really ECX register. It's just you know, how things are being viewed in Cutter. That's pretty much it. All right, so now if we check it, it says well done. So looks like we successfully cracked the serial code key here, and technically would be able to get in. Now this is an easy case because the serial key was hard coded inside of the developer's code already. So it was easy for us to just basically load that into a register and check. In other cases, you might see like an API call sent out to, you know, Windows API call sent out over like the internet to like a remote server that will where the license key exists and the check goes out over the remote server. It still is possible to crack those kinds of setups, but it is more complex, and you're now dealing with a lot more, you know, tedious lines of code, setting breakpoints and trying to figure out where things are. In this case, it wasn't too difficult to set breakpoints and try to figure out what's going on, just because it's a very simple program. So something to keep in mind on. Okay, let's keep going. This is fun stuff. Okay, let's do another lab. This one we're going to learn a little bit about how to manipulate some of the application components here. So for this one, let's run this script, and so you can see what it is and what the actual challenge is for this. Keep going here. Okay, so we actually just open this dialog box. It says, I'm a nag screen, please remove me. So we need to remove this box, and then we get this you know, this pop-up here, and then when we leave out of this pop-up, we get another box here. Nag screen, please remove me. So there are two other screens that we need to move, and this is basically just simulating like how to manipulate an application in order to do some more types of cracking, if that makes sense. So first, what we're going to do is that first nag screen. But before that, as always, I do want to run to, let's pause that. Let's go to the dashboard, just make sure we're still in the 32-bit architecture, the x86 architecture here. Windows, we are using, you know, B32, that's 32-bit. This is just some other information that we don't need at the moment, and Little Indian. So everything looks exactly the same as we need it to look, and we can go to the disassembly, and we kind of understand how the program works by running it already. So let's go to main, and then we're gonna go to the main graph where I like to go, and then we'll kind of figure out what's going on here. So in main, and this is, you know, I love the main graph because it kind of helps understand how things are going. So, you know, you start at the top, you have your main function, and then you have this Windows call, create dialog param A, and we could pop this open into you know, Google again and just look at the dialog param A, but it kind of self-explanatory, right? It's a dialog box that it pops up. And then Little Indian, we push the instance template name, and then, you know, going up the next parameter here, and then, you know, the last parameter is just pushing 0 to the stack there. All right, so now we know once we call this dialog, we do some kind of comparison with 0 and whatever is in this I guess we can call this like a variable here, whatever is in this D word, and then we move whatever's in EAX at this moment to this D word. So we move the value here to wherever this variable is in D word here. And then we have a jump condition, and if this condition evaluates correctly, so in this case it's if not equals. So in this case we'll say if this evaluates to the if the if not is equal to true, then it will skip this block here and evaluate past here, and then go down to this CMD function. If it's false, it goes and this box here, and entering this box pops open a message, and the message contains strings that look pretty familiar for this one. But what we'll do is this: we'll identify this by we'll say we want to see what's in this box. So we'll do it this way. We'll set a breakpoint somewhere here. Actually, we can just open this, so we can copy this address, and then we can look at it in a disassembly here. Okay, so we can look here. So this is the jump before it starts going through other things. So we can actually, this is jumping to 1044, which is here, there, which means I am a nag screen. Please remove me. Sorry, this is, so if this jump were to evaluate true, it would jump here, 44. But because this dialog box is popping up, we assume that this jump is actually not evaluating to true. So it's just continuing to go down. So what we can probably do is we'll set a break right after this message box here. And then we'll run it just to make sure that this is exactly what we need. So boom, okay. And then our breakpoint gets evaluated. And then from here, we can look at the registers, see if there's anything there of interest. And no, there's not. Okay. So from there, we just noticed that our box popped up. We clicked OK, and then it stops. So, and that box was the thing we need to remove. So we have confirmed that this message box is what we need to remove. We can run that again just to double check. All right, box pops up. As soon as we click OK, boom, we hit our breakpoint, which means the last call that happens is this message 8 box. So we know this is what we need to get rid of. Interesting. There are a few ways to get rid of this. Actually, we could let me pop this back in. Let's take this breakpoint away. We can probably just no op this function call here. Basically what we're doing is just kind of like adding, like zeroing out like this actual function. So it's not going to evaluate at all. It just kind of just read as, like, we'll say read as almost like a null value kind of thing, just for simplicity. That's usually called like a no op. So you just kind of like no operation, you're just telling this program to just do nothing when you get to this block here. We could do that, but looks like we already have a jump here, and we might just be able to actually evaluate this jump to true, and it skips over. So that jump actually skips over this block that we need to skip over. At the moment, it's not skipping, and this is jump if not equals. So actually, let's go over one thing I didn't go over in part 1 too well, were the different jump conditions, or the J conditions in ASM or assembly, the x86 architecture. Let's go over that actually, and you'll see what I mean. Okay, so these are your conditional jumps. Different types of jump instructions. The general type is J and P for jump instructions, of course. But when we talk about J conditions, we have other types of evaluated jumps, and you can think of these conditions almost like if then and things like that. So conditional based statements, in this case, conditional based functions. So JE is, jump when equals. So jump if, something is equal. Then you have JNE, jump when it is not equal. JZ, jump when the last result was 0. JG, jump if greater than. JGE, jump when greater than or equal to. JL, jump when less than. And JLE, jump when less than or equal to. You don't really have to remember this. You can always go back and reference what the actual jump condition is. But we did see that it was J and E that we were looking at. So jump when not equal. Going back to our assembly code, the question is jump when what is not equal, right? So generally, and I didn't explain this in the first lab, but generally when you see J and E, it is equated to some kind of flag. So we can, it's part of the E flag register. So in the E flag register, there are different flags, and usually you can like set a flag to match a jump condition. So we can assume that this is basically saying jump if the flag is not equal to something. So we'll say like if the flag is not equal to, 1, then do a jump, meaning if the flag is at 0, then jump. Or in this case, we can say if the flag's at 1, for example, jump. And then the opposite would do the exact opposite, right? If the flag was 0, then just kind of ignore this jump statement and don't do this. So there are ways to, in fact, there are some debuggers that will actually show you the E flags that are available. And you can go and change the flag from 0 to 1. Sometimes it shows multiple flags. You kind of have to play with it and see what flags, do what. In this case, it's actually a lot easier way to address this. And I like to do it this way. So what I do is I'm going to actually set a breakpoint here at this jump. And okay, we'll run through. Boom. Okay. So we know that J and E is jump when not equal. So all we have to do really is let's edit the instruction and let's set this to the exact opposite. So the exact opposite of not equal is equal. So that's it. Just kind of flip it, inverse it a little bit. That's what I like to do instead of setting a flag. It's just another way of doing things. So if we change that, so now it's saying jump if equal. So instead of the not equal, this should be equal because the flags have not changed. The E flag register has not changed. We haven't changed any values there. So if I were to continue, boom, it looks like I skipped the original dialog box and I go straight to this dialog. So we have successfully evaluated this jump condition and skipped over that initial message block. But when we leave this, we get the closing message block. We'll have to take care of this as well. So first, what I'll do is this. We'll pause here. We'll go to this here. And we only change that for that runtime. So I want to change this permanently. So JE, okay, boom, change that. And then I want to save this. Boom. Now update 1 is changed to for this jump condition. All right, now we have a second jump condition that we need to look at. So let's go back to the main graph. Okay, so we successfully moved past this. Great. We get down here, and then when we are here, we have another jump to this 10A4, and if that's evaluated as true, we get down here. If not, then we get some more messages, some more dialogue messages. Okay, so it's not clear or what the next dialogue message is here. So what we can probably do is go back to disassembler, run it, and see if we can grab it that way. Yeah, we can scroll down and look, but let's see if we can grab it this way. So let's run. Let's cancel this, and we don't need this breakpoint anymore. Remove that breakpoint, and then we can run. Let's see. All right, so we get here, and then we just boom get here. Here, I want to try using the string method. That's something that generally works. So you can just start, looking for I am. Boom. So you have a string method, and let's show the references. And you have, this is our jump. So this is the first reference. And if you can see, there's another address that contains this exact string. Well, this might be the last pop-up. So both pop-ups had the same exact string in it. So this one might be the last pop-up. And we see there is a jump. Please register me if you keep going down right here, closing tag. So, and it looks like this is a post quit message. So, this is being basically, just posting a quit message right after this, this nag screen here is evaluated. So what we'll do is we'll open this address. I can close that. All right. And so we're here. So it looks like this is where we need to be. This is where the next closing box is. So if we look up, we see a jump, but this jump goes to EC, which is here. And that's the register. So we don't want to change this jump because we do want to get here. And then after the register, we do a return. So it returns to like an address here. And then after that, we start going through a function call. And the function call we're going through is message box A, which I don't need to look up because it's self-explanatory at this point. And we push a string, and I think so little Indian style, right? You have the first parameter, then the second is just like the message, and then I think this is like the context box here, and then you just kind of go up. So in our case, we probably want to delete this call, and that should prevent the box from popping up. But because this call has parameters, so we have these parameters here, all these pushes to the stack. We also have to do something with the pushes. So generally, to delete a call, all you have to do is add a nope there, no op. So edit no op. There you go. So all that does is take the actual function call and it just says no operation, so do nothing. But right now there's an issue because now we're pushing things to the stack and we're not making a function call in order to interact with these things in the stack. So it's inefficient, one, and two, we might have some issues later. Another thing that we got to be careful of is making sure that we don't touch other function calls here, which we didn't, which we got lucky here. But what we're going to do is just highlight all the pushes right after this call, and we're going to add more no op instructions. Boom, no op. This again, I thought I can just highlight all of it, but I guess we can't. So we changed the jump condition in one, and then we did this way. We could have actually just did the no op for both, but I think it's easier to show you how to change the jump condition as well, so that there are cases where you'll need to do one over the other. Okay, so function call, we stop doing operations here, and then we do another function call, which is the quit message. So let's save that. Now, if we run it, of course, actually, we were running that in the, we weren't actually doing that. We were running that in while the program was running. So just in that context there. So we actually need to do that again. Okay, so now we can save it. And if we run it, click OK, and we just, run the program, see this, which is what we need to see. Remove the nag screen. So we move that to start. Take a look at about, that's fine. And if we leave this, we shouldn't see this ending screen. And no, we don't see the ending screen. The program finishes. All right, so we have successfully modified this. So now it should basically we bypass that beginning screen and also the ending screen. So when we look at the main function here, the jump we changed here, and then as you can see, the graph's a lot small. There was a box here that we did no operation, so it's not actually going to evaluate. And that's it. That's this lab on how to manipulate the application so that you're bypassing some of these things. In this case, it was just like a nagging screen. In other cases, you might have like a license check, and then that license check might not be validated. So if you can skip the license check, for example, then you can have like, software cracked and there's no other additional checks, for example. So that's something that absolutely look at, see how the application reacts to you just jumping over a license check or skipping it. Or sometimes you might even see, if evaluated true, then continue kind of thing. And if you see that and you're seeing that the application is evaluating to false by default, just try to change that jump condition. So instead of a JE, change that to like JNE, or vice versa. Or instead of, if you see like a regular like jump JMP general command, try to change that over to like a JNE and see if it'll evaluate based on some flags, things like that. I hope you enjoyed the labs that we just did. I love doing it. It was extremely fun. It was nice to just go through some things. I hope it was easy to understand. If not, let me know. We'll make a part 3 and start making this a lot easier. The purpose here is to make it fun for all of us. Reverse engineering is actually a very difficult field. I have only scratched the surface with a lot of this stuff, but it is very fun, and we as people just miss out on all that fun. So I hope this video can kind of spruce it up a little bit. If it did, remember, like, comment, subscribe, get this video into that algorithm. Leave suggestions. I'm looking through those comments. I'm looking for some nice, cool videos to make. Feedback. I'm looking to improve. All the above. This is what we do. And lastly, this information, keep it ethical. You know what I mean? Don't go out here cracking, reversing everything known to man. I'm looking at you guys who's looking to get tools, bug bounty tools, and paid software, looking to get that cracked. Yeah, I'm looking at you guys. Don't be doing that. Don't be doing it. Let's keep it ethical here. All right. Hey, appreciate you guys. See you in the next one. I hope. Pap out.